So maybe I can just start off with a quick question about there's maybe a perception among the broader robotics community, or maybe your PhD students, that these sort of symmetry-informed methods have a high barrier to entry, whether it's because students, in engineering at least, don't typically take, representation theory and differential geometry, things like that. My question for all panelists is, do you view this as a real or perceived barrier? And either way, what can we do to sort of reduce it?
Or one of mine. So I think it is a real barrier. I think there is a significant overhead in just the mathematics of geometry and symmetry. And look, I've been in this field since 1995, something. So it's sort of been my whole career. The reality is that when the theory yields significant actual real-world performance, people will learn, right? So, it's always been there. In the equivariant filtering that I've been doing for the last 20 years, for the communities where they actually care about performance, people will learn the theory because they can see it works. And what we're seeing today is in machine learning, for the problems where it significantly reduces the complexity of the actual learning, it works, people will learn it. And that's the reality of the situation. And you can't expect the community to learn complex mathematical theory for no reason, but it works. And
yeah, make it work for time for sure. I see Robin has a hand up on the virtual speaker panel, so maybe I can go to Robin next.
Thanks. Yeah, I think one of the reasons I've gravitated towards robotics is that I think roboticists are particularly well equipped to use equivariant methods. Like in the general deep learning community, when I tell people what SE3 is, they don't know, but roboticists know. So to actually develop these methods further, the details does require some background, but to use them in your problems, I think a lot of people already know what they need.
Thank you. Justin, you seem like you wanted to add something too.
Oh, yeah. It definitely seems hard initially, just like learning a new language, but if you put enough time and effort into that, eventually you'll catch up.
A little bit to add on, I think today's workshop covered a lot of area in robotics, like perception, estimation, also control, and different areas they have their own ways of doing and implementing it. And if you're specializing in only one area, you can focus on that area of symmetry and then focus on learning your expertise, and that will reduce your time of this learning curve. So I think that will help.
Thanks. Did any of our other virtual speakers want to add anything to that? Or we have a question in the audience. So, can you come up here actually so people online can hear your question? That's thank you.
So that purpose, I am writing a particular paper about this to the global learning. So my name is Tzu-Yuan, and I'm working in Professor Robotics and Professor George Chien at the university. So stay tuned. It'll come in 3 months. Okay.
We'll stay tuned. Thank you. I think it's a good point though, not all research is written to be tutorial, to say the least, right? So the more we can create those kind of resources is a good thing. Another question I wanted to ask is, there's lots of places structure has been exploited in robotics, but my perception is that often it's more limited to one particular area, like graduate Hamiltonian methods in control, or projective geometry and vision. But symmetries have this really cross-cutting impact. I'm curious, this is maybe a bigger ask, but are there any areas that panelists see other than symmetry that they think might be right for a sort of multidisciplinary impact in the future? I don't have an answer to this one, so maybe you won't either. But.
So you're asking an area that is in symmetry that will have impact.
Sort of another structural property that might have a similar rod.
Study the classical non-elephant animals, right? This is sort of like infinitely large. It's hard to say, right? I mean, actually there is something that's worth saying to try and get into the space, right? So the point about making progress in complicated systems. So I do a lot of work in nonlinear dynamics. And so if you try and study nonlinear dynamics, it's too hard, right? A general nonlinear system is too difficult to actually really do anything that has real world impact. So what you look for is structure that you can exploit. And there's a number of different structures. There's linearity, there's polynomial type structures, there's all sorts of different structures out there in dynamics. And one of the structures is these geometric symmetries, these equivariant type symmetry. And so really what we're doing at the moment is we're finding a structure and a class, that structure applies to a class of systems, real world systems that is interesting. It's not a null set. And then the question is, can you exploit it? And that's what symmetry is done in this case. So you have to find the same thing. Yeah.
Maybe we'll go to, Elise just put her hand up. Maybe we'll go to Robin then, as we say that.
Yeah, I think of equivariant neural networks as basically encoding the inductive bias that the latent representations live in some group representation. So one way to sort of like generalize that and look for other structure is to consider different kinds of mathematical structure that you can see in latent representations. And to some extent, various people work on that to different things like metric spaces or Riemannian manifolds or other kinds of geometric structure in latent space.
That's a good answer. I like that question a lot. Anyone else from the panel want to add to this question?
I agree with what Robert and Robin said. I think what can help is that we add some knowledge to the system, and that can reduce the computational cost. And this knowledge is like, if we know this system is going to obey this rule, why not? Yeah.
That makes sense. Can I ask anyone in the audience if they have questions they'd like to ask the panel? I want to direct you. Oh wait, sorry. Elise had her hand up. I want to get her answer real quick. Hold on just a second.
Hi.
Go ahead.
Can I speak? Yeah, sorry. I have a hard time hearing, so I never know if I understand the question correctly, so I'm going to try. I think I really like Robin's answer. I don't really have much to add to that, but if I may, I heard the term interdisciplinary, so I want to maybe zoom out and go in the opposite direction there for a second. I think there's much to be learned from interaction with, for example, natural scientists. That's, at least I'm learning a lot in my current, I'm working on AI science now, and this has been super useful. One of the things that I learned there is that there's lab robotics where they're using robots to do lab experiments for chemistry experiments and stuff like this. That's also an area where I expect a lot of symmetry to show up, and it's very, very interdisciplinary. So it's not maybe quite the spirit of your question, but it's technically an answer.
That makes sense. Thanks for sharing that. Okay, let's see this next audience question.
Okay, so this workshop is about Cynthia and Equivariant, and we're talking about how good it is to the research field. I just to open the discussion. Why would, like, what's the bottleneck to try to use Equivariant? Like, we have seen some research questions, but there seems to be some directions to try stuff. But what would be the bottleneck?
Anyone want to take this one?
All right, so I can say something about it. I can see a couple of different answers to this, but one thing is, I think you're seeing at the moment people figuring out how to utilize the structure to be able to do something exciting, right? So we've been working on that in dynamics and filtering for quite some years, and I think actually there's some really well-established theories for how to make very efficient filters, like the invariant extended current filter and the equivariant filter. These are well-established theories now. And what we're seeing in the machine learning is it's much more recent that people are going in there, but we can start to see some of those ideas come about. So I don't see that as a bottleneck so much as the natural part of science. There is one real bottleneck, which is was partly addressed by some of the speakers today, which is that at the moment finding symmetries is actually something that people have to do by hand. So you sort of need to think about the problem and then you have to find the symmetry. And it's not actually so unreasonable because the physical system has it has a representation, it has natural symmetries associated with it, and it's a modeling problem, not necessarily a data-driven problem. And having said that, there were a couple of comments about data-driven symmetry finding stuff, and so that's all open at the moment. But I would say that potentially is a bottleneck. Certainly in my career, the last 25 years I've been working in this area, we have been, I gave that slide, those two slides, you know, we found the SO3 symmetry straight away. It actually took another 4 years to find SE23, took another 5 or 10 years to find the tangent space of SE23. Homography we found reasonably easy for SO3. So these symmetries have taken a long time for us to actually realize and understand and start using.
If you welcome, I want to say that even if you realize the symmetry in the machine learning world, if the groups are different, then you need to design a different network for each group.
Yeah.
So this is like a kind of one bottleneck that I see. Yeah, I don't know if somebody wants to add on that.
I can add some. So another bottleneck I think is the break of symmetry. A symmetry actually it's not fully symmetric. And this can happen by the perspective changes of collision or things like that in terms of robotic perception. So that's also something that we need to address. Basically, that's a break of the rule. Like we have some symmetry rule embedded into the system, but sometimes it doesn't fully satisfy this rule.
We had a hand up from Robin.
Elise mentioned it in her talk, but I think the biggest bottleneck for equivariant neural networks is computational efficiency. So that's the thing that I think needs to improve for wider use.
Computational and memory. I think Elise said something about speeding up also. That demonstrates some.
Yeah, I actually don't think that designing neural networks to be equivariant to different groups is a big bottleneck. I think a lot of the main ones you would encounter are already there. And there's also automated ways to construct these neural networks now. But I agree with Robin that computational complexity is kind of a big one, especially if you want to act in real time. But I also know that there's a lot of people who are aware of this and are working on this. So it's definitely not being overlooked by the community.
Very good. Audience question?
Audience question?
Yeah.
Audience comment. So when one has an overhead camera and doing manipulation in the plane, SE2 equivariance, no problem. But in 3D with occlusions and things, I think it's a big problem. So if any of the panelists would like to address the occlusion problem for SE3 equivariance, I'd like to hear the answers.
It's a great question.
It's in the light variables.
Go ahead, Robin.
Thanks. It's a great question. It's a great point. In some sense, you know, if you have partial observability, even if you're dealing with a point cloud and there's occlusions, then there's a difference between the way what is SO3 doing? It's rotating both the scene and the camera, right? Because if I just rotate the scene, then the points move and the occlusions stay there. So that's the kind of thing that we would call like the extrinsic equivariance in our paper. And then how to approach it? Well, like in some of our papers, we just plow ahead with SO3 equivariant methods, and we find that they work pretty well. It's just that you're not getting the full advantage of the SO3 equivariance because of these extrinsic factors, so it reduces performance somewhat. As far as like more directions to address this issue, I think it's like a great research direction. The computational bottleneck in SO3 is also a big deal, especially when dealing with point clouds.
Thanks, Robin. Did anyone else want to comment on that?
Adding a little bit, so for that's really a big question for SO3 changes and safety. If camera also changes versus like 3D point cloud changes, and also, for example, you only measure the front of the object, that when they rotate the back of the object, and this is nothing you have seen before. Those kind of challenges I think has been challenging for a lot of cases. And one thing is, for example, considering that could be for point cloud, that can be low overlapping situation. You can think of other ways of dealing with that. And some papers that are not equivariant, but they're thinking of like using diffusion to accompany like the missing part that we cannot observe, and maybe adding that to equivariant numbers can help understanding the whole picture.
One thing that usually mitigates this problem for users is compositionality. Like treating your scene with smaller sentences or fewer objects. So even if you extract a signal, even if it's not like, even if the whole scene is transforming, some parts of it are locally transformed. So your extraction will still be consistent, at least for these parts that can be described as local transformation. And that also goes to some principle that Jack was asking before, that is penetrating also, which is compositionality. Sometimes this is not as rigorous as the symmetry, so we try also to have like theoretical parts writing down rigorously in some applications, and we saw that the symmetry penetrates. But there are probably other directions that haven't been established because they lack theory. So that's also a good thing that the theoretical contributions are really valuable because it's safe.
I think for the sake of time, we might have to close our panel discussion there, but we have one major active business to finish it, which is the rest paperwork. To do so, I need to ask the jury of judges to meet me in the hallway for 2 minutes if they are final decision. So if you can all bear with us for 2 minutes, we'll be coming back with the rest paperwork. Okay, folks on Zoom can see my slides. Looks like it. So just to close off the day here, I want to really acknowledge all the people who put their time and effort into this workshop. I really appreciate it. First of all of our keynote speakers, analysts, and award judges, I really appreciate you being here, whether it's in person or virtual, spending time to share your ideas about these exciting topics. I'm so impressed with the content that everyone brought to such a, so many different perspectives. It's really fantastic. So thank you so much. I also want to thank everyone involved in the organizing committee. All our friends for putting this together and doing possible on about 13 doing it. And lastly, I want to thank you guys all for coming and for everyone who contributed to the poster. I want to plug one more time that this workshop is sponsored by the technical committee at Equivariant Businesses. So if you want to join or follow them, you can do so at the links there. And to conclude, we're going to be giving you the Best Poster Award along with a $200 prize sponsored by that committee. To contact Rich, SC3 Equivariant robot manipulation, task learning via geometric instance control. Any authors of that paper come up to take a photo. And that's it for the workshop. Thank you guys so much for participating. Really appreciate it.